Hello everyone, welcome back. We have as of now derived equations for conservation, and we already reviewed. There is no more of review, we are already entering gas dynamics from now. It is the, I believe, the 4th class, so we are on time. Okay. So we are going to start with one dimensional flow. Okay. In reality, no flow is really one dimensional. So you have to now think about what is one dimensional flow, and then once we understand what we are talking about as one dimensional flow, we will go into deriving again equations for one dimensional flow. Okay. What we are going to do is we will start with the original equations we derived all this time, simplify that to go to one dimensional. After that we will mostly use only one dimensional equations, nothing else. So what do we mean by one dimensional flow, and why is it a useful thing to go for? Any ideas? Let us answer the first one. What do you mean by one dimensional flow first?
Flow parameters are a function of only one direction.
Flow velocity has a unique direction.
Flow velocity has only one direction. Flow properties are function of only one direction. Okay, those are all like very constraining terms. Okay. Let us look at the other thing. When will I use a one dimensional flow approximation? Then we will get back to this. When will I use a flow? When will I call a flow one dimensional? Flow through a duct, as in you are thinking a straight pipe, or can the duct be curved like this? It can be curved also, and we can still use one dimensional flow. Areas should not change, you are saying. Okay, I do not want to accept that fully also. Okay, but okay, now we will go back to my way of looking at it. So I am going to say there is some general flow through a duct. We will start with flow through a duct, simple enough. Some crazy shaped duct, I do not know what shape it is really. Let us say it is something which is having area changing, and there is flow inside this. Okay. Let us make it slightly nicer than this, something like this. Now I am going to say my flow is entering this way and is coming out through this. In reality, what it is doing is it is going to have a boundary layer, which means the velocity profile is not this top hat profile or uniform profile as we have drawn it. It is going to be more like this. Towards the end, the velocity will go to 0 on both sides. This will be more like the actual velocity profile there, and the same thing will happen here. Let us say I will draw it one section before. It is going to be some kind of velocity profile. Do not worry about the integral not being same, it should be the same, but I have not drawn it correctly, that we will not worry about right now. Okay. Anyways, so if this is the flow and I am not really worried about the change in this direction, the perpendicular to the main axis of the duct direction locally, I am saying locally, very important word there. I am going to say at this point this is my flow direction, at this point this is my flow direction. I am not worried, as long as I am going to say when the flow is here this way, flow everywhere here is only this way. That is, I am not having any huge recirculation flows inside. If I pick a case more like this, if this is my duct, then most likely the flow will just go straight with a huge recirculation sitting here. How do I know this? You should know some fluid mechanics. Okay. This is not fluid mechanics course, I will not go into that, but If this is the case, now if I take this point, flow is not always going in one direction, okay. And if I take this point, this velocity is significantly high, or it is at least of the order of this velocity here, okay. So those are things which I cannot neglect. This flow is not really one dimensional, right. When I look at this flow, it is not really very bad. If I look at any cross section, flow is roughly going perpendicular to that area of cross section, nothing else. And if I am willing to neglect the changes near the wall tips, near the ends, I am going to say it is not really changing, is changing in say 5% of my area or something like that, I will neglect it, or I am not interested in that change, then I can replace this velocity profile by a flat velocity profile with equivalent mass flow, okay. At this I am removing the center velocity a little bit, adding it to the corner, so that my masses are same. The mass that is actually flowing here is imagined by me to be flowing in this corner, so that the velocity profile is uniform. That is the way I am going to look at it. This change I have drawn it exaggerated, it will not be really this big, it will typically be very small if it is just a flow through a close to one dimensional duct, okay. I did not tell what the cross section shape is going to look like. If I take this cross section and look at the shape in front of me, it may be looking however crazy it feels like. This may be the duct cross section, I do not care, okay, as long as the flow is going only perpendicular to this duct, this area, nothing else, no other flow. That is my assumption currently. Typically if there is such a flow, nobody will want to use 1D assumption, I will also tell you that. Typically they will use it only for something less crazy, more like this. They can use 1D assumption for this is a lot more complex, there will be other effects which I am neglecting here, that is for fluid mechanics people to teach you. But if a flow is going to have such things, here the velocity will be pretty high, and I cannot neglect this velocity with respect to this one. So in this particular situation I cannot use 1D, at least in this area. But if I do not care, if I just say I am interested in this section and interested in this section, I can probably use it, okay. Depending on what my interests are, I have to think about using this, okay. This is just simple example of 1D. Now I also told I can think about it as stream tube, somebody said, I do not know, but I like stream tube way of looking at things. Why? What is a stream tube? What is a stream tube? If I form a duct with a whole bunch of streamlines together, how will I think of it easily? Let us say the flow is currently through the board, and I am going to draw a closed loop on this board. Now there is a whole bunch of streamlines going from every point into the board. If I go on the other side of the board and see all those lines coming, those streamlines together will form a tube, and there is no mass that is going to cross this line, right. That is the way I have to think about it. Oh, I will think about it in a better way, flow is coming from inside the board towards this side, easier to think about. So I am going to say there is a whole bunch of streamlines coming out from here, wherever, whichever direction they are going to take, but overall I will keep all of them connected the same way, they cannot cross, right. So this circle may change shape to something else, yes, it may become something else like this somewhere else. When it comes to this section it may have a different shape, but the streamlines would have never crossed each other. That is a basic rule in fluid mechanics, it cannot, right. So I do not need to worry about what happens, the tube remains as a tube, flow inside will remain inside, the mass that entered inside this circle will stay inside this whatever new shape we are having at some other distance, but it will not go out. No other extra mass from outside has also come inside this, no exchange across this. That is why it can be imagined as a tube, it can be imagined as a physical tube sitting there. The advantage of using this is I do not need to worry about walls and having boundary layers and other effects. that does not exist here. Okay. So, I can imagine a flow fully through this whole room, no boundaries, no walls nearby. Still I can imagine a circle here and say all the streamlines going through this, all of them will form a tube. That tube can also be used. Okay. That can also be a stream tube. Okay. Now, I will imagine this as my stream tube. Now, I will go back and use this as a stream tube, and if I can say that in my wherever I am interested in that particular cross section, there is significantly only velocity perpendicular to this area and not along this plane of the area any other direction. If that is not there, or I am willing to neglect that particular flow. Okay. Neglect should be like reasonable neglection, it cannot be like it is 100 meter per second, the main flow is 5 meter per second and I am neglecting 100 meter per second. That should not be the case, that is not really neglecting, it is ignoring. We do not want to ignore, we just want to be able to neglect. If there is such a flow which we can neglect, okay, then neglect the perpendicular components, the along the area plane component, if I can neglect, then I will consider that kind of flow, and that is to be valid everywhere in this whole duct or your stream tube. Okay. If it is valid everywhere in your stream tube, then I can consider that kind of flows to be one dimensional flow. Okay. Now, the next thing, is there any practical flow that will have such a thing? 1D flow, jet exhaust. Think about it, no flow will be really that. Okay. The reason is, I will take that particular example, jet exhaust. I am going to say there is some nozzle, this is the exit plane of the nozzle and there is jet coming out. It will not be just going straight. What will it do? It will start mixing with the outside, and this region is going to have shear layers, eddies forming, all kinds of vortex rings formed, whatever, depending on the Reynolds number. So, the flow is going to be doing all kinds of things like this. You would have seen pretty pictures like this on the web or in fluid mechanics books. Okay. We do not want to go into details of it. If I think about a particular streamline, this is not really a streamline I have drawn, I have not drawn a streamline really. Okay. It is probably not even a clean streak line, it is something else. Okay. If I draw streamlines, it will be looking sometimes going this way, sometimes going this way and all that. Okay. So, this flow is really unsteady, but can I neglect is the question I am going to ask again. There is some deviation of my, I will consider this as a stream tube, no, the straight thing. If the flow is just going straight like water from a tap, water from a tap forms that nice stream tube, by the way. Okay. Flow inside that is all inside that stream tube formed by edge between water and air, nice example. Okay. So, I am thinking about that kind of stream tube, but the edges are shaking, oscillating. You would have seen this again in water if you increase the flow rate a little more. Okay. If I am willing to neglect those changes, I will say in real life it is not exactly forming that straight thing, it is oscillating in time. Okay. But it does not affect my understanding, or it does not affect my particular study, it does not affect what I am interested in. Then I can still say I will just draw something along this line. This is what typically all the shear layer people will do. They will just draw some average line that way and this way and say my jet grows at this rate, and then they will just talk about growth rate of a jet and just worry about such things. And we can imagine that kind of thing as an average line. Now, we will just think about time averaged quantities. I am not interested in instantaneous values. If it is instantaneous, maybe my stream tube would have been curved crazy, something like this. We are willing to neglect that. Okay. That becomes your close to 1D, not really 1D, but we will assume it to be 1D. So, we will call that the quasi 1D problem. Okay. Actually, it is quasi static 1D problem, quasi stationary 1D problem, whatever. Okay. Now, There are other simpler examples which are more common to gas dynamics. Okay. Flow through a nozzle. I have a flow that is going like this, coming back out like this. Of course, there is a wall that is going like this, and inside that there is flow. Now, I am going to assume that the flow tracks the wall. By the way, if there is separation, the flow does not track the wall, then there will be recirculation zones. That flow cannot be really considered as 1D. Why? It will have the same problem as this recirculation zone. It will have the same problem. This velocity will be comparable to this. I cannot neglect this. Okay. We will go back here. Let us say we will not have separation, we will have nice flow, and the center line streamline will just go straight. If I have a flow like this, at any cross section, at this cross section it is really nice, all the streamlines are perpendicular to the area, nice, my assumption is perfectly valid, no problems. Here again it is again valid, everywhere flow is perpendicular to that cross section area. At the center also it is valid. Is it really valid here? Not really valid here. Okay. The flow is having some other component that way and other component this way. When it is having these components, am I willing to neglect that, is the question I am going to ask. I am going to say the actual velocity this way is very small compared to the velocity component this way. Okay, I am going to split this, actual velocity vectors will be more like this. I am saying this velocity is very high compared to this velocity, I am going to neglect this component, and I will assume that my flow is going straight parallel to this. Will any real flow do this? No, it will always follow the wall, but we are assuming that it is going straight and still follow the wall somehow. We will not talk about it still following the wall, we will not draw this kind of streamlines in 1D flow. Why? It is 1D, there is no streamline concept in 1D. 1D all streamlines are parallel always. Okay. Only when there is 2D I can think about a slope really. 1D there is no slope, right. Hopefully you are comfortable with that. Dy by dx gives you a slope, y and x should be there. There is only x, there is no slope really. I can just talk about velocity gradient along this, that does not give you a slope, and so you do not get a streamline. Streamline needs slope of velocity vector to draw this, or slope of the streamline gives you the velocity vector direction. Hopefully you know this. So, we cannot define a streamline in 1D flow, and we are going to assume such things here. 1D here we are going to say this is clean, very easy to assume here at this junction throughout. When I go to this diverging and converging area cross sections, there things may not be very nice, but we will assume it is close to 1D. Again we are going to call this the quasi 1D flow. Okay. The previous one was we are assuming that it is not very steady, but we will assume it to be close to steady, that is I will call it quasi stationary. Okay. Now we will go to the next thing, and I am going to say it is quasi 1D flow. We are approximately saying it is 1D flow, it is not really 1D, I am neglecting the perpendicular to streamline direction components. Okay. Now, when the velocities are very high, there is one more thing we need to worry about in real flow. What is that? In real flow velocities are very high, something else, turbulence. Okay. We are going to neglect that also in here. Okay. We will not worry about turbulence, we will just say turbulence may have its effect, but that is not as high as this main component of velocities. There will be some fluctuation of my velocity up and down in time, we will say that fluctuation magnitude is very small compared to my main velocity magnitude along my 1D direction. So, we will consider only that and we will ignore those small things. Okay. So, it looks as if it is steady, okay. It is actually quasi 1D problem, so it will look like it is very nice and steady, but we will not pick up any unsteady problem as such right now. We will go to unsteady problem towards the end of this course, last 2 lectures or something we will do unsteady, okay, where I am talking about suddenly I opened a valve through a nozzle, what happens? We can even look at some pictures from one of my students research. I think we can look at that when the time comes up. Okay. Those are all possibilities, but we will start deriving equations for steady one dimensional flow. For now we will stick to steady problems. Okay. Of course, we have already neglected the fluctuations in velocity perpendicular to those main line. What if the main line itself is varying at time? We are going to neglect that right now. Okay. So, we are going to simplify the expressions and then start deriving mass equation, momentum equation, energy equation. Okay. Now, I want to go revisit control volume. What is a control volume? We already did this before deriving all the equations. It is some imaginary volume, some surface we are going to use, okay, inside the flow field, which is going to mark the region of interest for us, and we are going to study what is happening inside that volume. Okay, that is what it is supposed to be. And I already told that it is an art in picking what control volume we want for a given problem. It is an art, and if you pick the correct control volume, our equations may get simplified. If not, it may become very complex. We will see that in momentum equation today. So, we will do two kinds of control volume in all the problems, okay. Two types of control volumes. One will be, let us say my flow is like this, some such flow. I can put a control volume something like this. It is roughly a stream tube forming my control volume, that is a possibility. Or I could take some perpendicular plane to all the streamlines and a very close to it another perpendicular plane, and I will connect them here. This could be my control volume also, very thin slice of control volume. I can choose either the big control volume or the thin control volume. They will give different kinds of equations for conservation. Okay. If I do this big thing, I am going to talk about what is happening inside this whole volume. When I talk about this very thin slice, I am going to talk about what is the change that is happening at this point. Okay. One is going to talk about integral form, other will talk about differential form. That is what it is if you already know something about it. If not, we will go and look at it now. Okay. There are two forms that are possible. So, we want to start with mass equation. We want to derive mass, momentum, energy equation today itself. We will finish all that out today. Okay. So, I want to go look at a little more detail. I will pick the big control volume right now. I will keep the other one, but I won't use it right now. Okay. Let us mark my control volume edges. The big control volume. My control volume is ABCD in this case. It is a volume, I am going to assume it is going 1 meter inside, whatever, unit distance inside. Okay. So, the normal is this way here, here the normal is here, in here the normal could be some other place. Okay. So, something like this. Now, when I think about fluxes, we always have this term, right, u dot n ds. This is related to flux. Okay. So, when I think about flux here, this is actually mass flux related. So, it is not really a mass flux, it is actually volume flux right now, we won't worry about that. Okay. We will get back to this. Actual mass equation has this, momentum equation has this, energy equation has this, every equation has. So, we are going to start here. we want to see what this quantity looks like first before we go to equations. At this point flow velocity is this way, n vector is this way. What will that give me? It is 1D flow. So, actually flow will be aligned along this normal, right. By definition of 1D flow we said perpendicular to the cross section flow goes. So, perpendicular to the cross section is where the normal direction will be. So, you are going to get to that point. What will this value be? U dot n value, it will be minus u magnitude, okay. Minus of u magnitude will be what it will come out to be. On that side it will be positive of u magnitude at this point. It may be different from here to here, it may be different velocities. What about the top? Let us pick this point. What will it be here? It should be 0. Why? I chose my control volume such that my control volume edge goes along a stream tube. I picked my control volume such that the streamline is parallel to the edge, which means this normal to the edge will be perpendicular to my streamline, which means my u dot n will be cos 90 0, right, that will come out to be 0. So, this u dot n will be 0 on this particular control volume. I was smart enough to choose such a control volume. That will be the same answer here, same answer here, same answer here. Always I chose along streamlines. That is a good thing about choosing stream tubes as control volumes. Okay. So, we will keep such control volume. Now, we will look at the mass equation. I will start with already derived equation. We had this particular form, we had so many forms, I am going to use one of them. We had such a form, okay. Before we made it into volume integral, we had this form. This is the integral equation, and then we said it is a steady flow. We are going to neglect this. There is no gradient in time. We said we are going to look at only steady flow, and then now we are going to look at this. I have to integrate this over all the surfaces, and it is a 1D problem. My all the other surfaces, all the side surfaces are all going to give me u dot n as 0, including this side surface and the back of the board surface, they are all going to be 0. Only this perpendicular cross section thing will remain, only those terms will remain. Okay. Now, I will label these sections as 1 and 2. Now, I can write this integral value exactly, because it is going to be one value for each section, u dot n will be one value for each section. Okay. So, I can write that value to be minus rho 1 u 1 a 1. How did I get this a 1? As the cross section area at section 1. How did I get that? This is a constant value at that section, density is constant at that section. Why is it constant? 1D flow. Okay. This whole region there is no variation here, that is my 1D flow assumption anyway. So, I am taking it out of the integral, sorry, taking it out of the integral. Only thing is integral s ds, that is my total area of my cross section, that will be my a 1. Why did I get this minus? U is this way, n is this way, cos of 180 will be minus 1. Okay. I get to this form, or equivalently I can say take one of them to the other side and say rho u a is constant. Okay. From section to section I can say rho u a will be constant. From one section 1 to section 2 I am going, rho u a cannot change. What is this rho u a? What will it come out to be? Mass flow rate. How did you get that? Area times length per time area times length per time is volume per time into mass by volume will be mass per time. Okay. You can actually prove that it is exactly mass flow rate. This is just dimensionally I am showing it to be mass flow rate. Whatever I told can be thought of as from here to here, if I go with same cross section, it will sweep that much volume with that density. That will give me how much mass went past that area. I will keep that as an exercise, you guys solve it by yourself. It can be shown to be mass flow rate exactly. So, I will write this as m dot equal to rho u a equal to constant. Very important relation for gas dynamics. Okay. We will keep this is your mass equation if I think about using a big control volume along stream tubes. This is one expression. Now, we will go and use this small control volume. I will draw this control volume again. I am going to say control volume changes area differentially. A small thin slice may have a new area after that, A plus dA. Okay. dA can be positive or negative. If it is negative, it will be shrinking. Currently, I have drawn it as if it is expanding, does not matter. Now, I am going to say it has some particular density, density would change by d rho. Any of these d quantities could be positive or negative. We do not need all of them. I can still write temperature goes to temperature plus dt. We do not need all that, actually we need only A rho and u currently. Okay. Now, all I have to go is start with this point. I know this is true 1D flow. I will start from here and apply this to this particular control volume. That is the easy way of going. On section 1 for me to section 2, the other side of my control volume. What am I going to get? Rho u a equal to rho plus d rho multiplied by u plus du multiplied by a plus dA. Okay. I will get to this form. Now, if I multiply it out, I will get a rho u a here, that will cancel with this rho u a. I will also get a lot of differential terms multiplying each other. D rho du dA is one term, d rho du a is another term. Like that, there are so many terms which have multiple differential terms multiplying each other. Now, we will neglect those by saying du d rho is very small compared to rho u. So, I will neglect that term. I have to always say when it is very small, it is compared to something else. Okay. So, think about that. Okay. Now, I will keep only terms that have one differential term, that it will be a times u times d rho, that is one term possible. Like that, I can have rho times u times dA. Like that, I can have another term rho times a times du. By the way, there are only 3 such terms. I just named all the 3. So, we will write those 3 terms. And I am going to say it is equal to 0. Really, I have neglected some terms. It is roughly equal to 0. If I pick my control volume to be very thin slice, then I am more justified. Okay. We will keep it that way, it is nothing wrong. When I make this slice very small, this d rho will be derivative times this thin slice, d rho by dx times delta x. That will become your thin slice, very thin slice. That is the limit of calculus. Mathematicians are okay with it, so I do not think there is any problem. We can say it is close to 0. We will keep it as 0 for now. Okay. So, this can be simplified if I divide this whole expression by rho u a. But always keep in mind that when I divide by something, that quantity cannot be 0 ever. I am going to say there is always flow in my control volume. Reasonable thing, we are talking about flow. So, I can never have 0 flow. So, a reasonable thing, I can divide this whole thing by rho u a, this whole expression every term. When I do that, I will get to a differential form another very useful expression in gas dynamics. Of course, you do not need to go do this thin slice control volume and all that. I can always go back and use this expression and say I will take derivative of this. Okay. I will just take derivative of this with respect to anything, does not matter. I will just take d of m dot, that will give you that form directly. D of m dot will be equal to 0. Okay. I do not need this thin control volume explanation, but it helps in momentum equation. So, we will keep it this way, and then I can come from there to here by just dividing by rho AU. That is also a possibility. Calculus can also help you there. Now, I will go to, I have a simple observation here. Okay. Now, let us look at this expression. This is going to give you some physical intuition. I will keep on adding to this physical intuition, looking at the same expression again and again. We will look at this now. For incompressible flow, I can say that d rho is 0. Then I have this du plus dA, or du by u plus dA by A is 0. That means if I increase area, velocity decreases, if I decrease area, velocity increases. Where have I seen such flows? Everyday life. Water flow through a hose, end of the hose you pinch the tube, water will go faster to a longer distance, right. Simple common example. Everybody would have at least poured some water through a hose somewhere in your life. Garden hose, typical example, when you pinch the hose it goes faster, right. So, that will work very well if I say d rho is 0. We will go later and I will show you that there is a connection between du and d rho which will make it go the wrong direction if m is far greater than 1. Mach number is supersonic. Okay. We will look at that probably next class. I do not think I will reach there today itself, but we will go and derive momentum equation now. As of now, we are seeing that the simple connection what you have observed in incompressible flow is valid, but I can just observe that that is not as simple a relation anymore because there is a d rho in a compressible flow. We will look at more of this as time goes by. We will go back and start from that corner again, momentum equation. Okay. Now, I will start with a control volume that is nicer to look at. I have this control volume and now I am thinking about momentum exchange across this control volume, and we already have this expression. I will just start writing momentum. Momentum equation. I will write the full expression as we derived before, and then we will start simplifying things. Now, I will put here plus shear force plus body force and immediately make it 0. That is what I did before also. I will do the same thing here, make them 0. Now, I have my main expression, these 3 terms, and now I am going to say I am having only a steady flow, derivative with respect to time is 0. I will make that 0. So, now I have only remaining terms here. Okay. If I look at this term, we already said that u dot n is 0 on the sides because they are stream tubes, and in this surface it will be minus u magnitude, here it will be plus u magnitude. I am going to have flow in this way and flow out this way, and I am going to say flow is parallel to those surfaces there. That is the idea. So, I can write this expression without the integral anymore because integral will just become integral of ds, which will give me area A1 and A2 it will give respectively. So, that expression will look like I am writing it separately, rho 1 u 1 is this multiplied by u 1 with minus sign, that is here, and then a 1 is just integral of s ds there. Now, what about this term p n vector ds? If I look at here, n is this way, but there is no dot product. There is no dot product, I just have to keep it all, okay, that is all. But n is going the negative direction. I am going to think about momentum going that direction, okay. So, it is going to give me a negative force, that is all I need to think about, okay. So, that negative will cancel with this negative, it will just stay as positive for only this surface, because this surface has n on the negative x direction, let us say my 1D direction, and integral s ds, okay, that will just be this, and this other direction n is pointing along my one dimensional direction. So, that will give me just positive single one value. So, that will be minus p 2 a 2. Is this all? That is where we typically will make mistake, because in here we have neglected u dot n in these surfaces, but pressure can act across a streamline. There is pressure here, there is pressure here, and the way I have drawn my streamlines, if this is the pressure acting, pressure is always perpendicular to the surface and n vector is perpendicular to the surface, they are going to give you good number, it is never be 0, right. So, pressure will always exist. Now, the way I have drawn it, it looks as if it is producing a force in positive x direction, okay. So, let us assume there is some force there, I do not know the value, why? I need to know the exact pressure values here, this is the problem with choosing big control volumes. Let us say we will not worry about that part right now, I will just say the net effect of this whole side surface area everywhere will be giving me a force vector fx along this direction. Of course, my vector does not have a meaning, it is just one direction, vector is just one component, vector is just a number for me, okay. So, now I have that force going this way, I have to keep that force also, and that will be plus fx. By the way, every one of these terms is a one dimensional vector, okay. Think about it, we are just looking at x component of the whole force created by everything, okay. Momentum entering this way will give you opposite force, okay, like that every term, okay. I am having this whole thing. Now, if I just rearrange this term, it will look like this. This is my integrated form of momentum equation in 1D flow. Of course, remember this fx, this is what is giving you thrust in your nozzles, actually it is not really giving you thrust, it is going to give you negative thrust, but this is important term in that, okay. If you use this to find your thrust in your nozzle from throat to the exit CD nozzle, you will get negative force, okay. But we will not worry about that, that is not gas dynamics, that is propulsion, you do not need to worry about it right now, okay. But this is your momentum equation. If I say I have a special case where I am going to say A1 equal to A2, a very special case, now I am not even just 1D flow, but constant area 1D flow, okay, constant area 1D flow, I still can have area cross section shape varying, but the area cannot vary, A square can become a circle as it goes, keeping the same constant area. That is still okay for me. Okay. A1 equal to A2. If I assume that in that equation, and this will immediately tell me that my fx will be 0. Why? I will go back here, look at the picture. If this area is same as this, I am going to say this force is going to be not in this component, but perpendicular to it. That is not my 1D direction. Anybody wanting to stop me there? That statement is true if I have a single constant area cross section duct. If square becomes circle, things may change a little bit, but if you think about square becoming circle, they will cancel each other. One place it will add force, other place it will remove force, there is no net force you will see. Okay. Overall this is correct. I am going to say perpendicular force is no more adding to my x direction. My only one direction existing is called x direction. Let us say that x direction force is not going to be added because it is perpendicular now, it is no more in the x direction. So I can say that is 0. Now my term becomes very simple. Remember this term also as a momentum equation, integral form of momentum equation in 1D flow, constant area flow. Okay, this is a very special thing. You cannot use it for any other case other than constant area flow. Okay. Remember this. This looks very close to your Bernoulli's equation. Okay. That is where things go wrong. Okay. If I let's go to differential form and then we will think about Bernoulli. I do not think I have time for Bernoulli right now. Okay. If I look at my that small control volume, I will draw it again. And of course we have A becoming A plus dA and every other term like that. There will be rho becoming rho plus d rho, everything is there, u becoming u plus du. Now I am interested in finding this force here. Okay. What will that force be? It will be having an average pressure between this and this. What is the average pressure between this and this? P plus dp by 2. So I will put that specifically here. P plus dp by 2, very very important. Okay. Same force here, same pressure here, sorry. What is the area on which this P plus dp by 2 is acting? It will be just the dA. Okay. Why? I am thinking about only this component of it, only the parallel component. Say I am imagining looking at a cone, a frustum of a cone, say a conical bucket. I look at it from the bottom, small area becoming big area, and I look at it and I push along this cone. Only component that matters is along the axis, let us say. Then what matters is only that annular region which I see from bottom of the bucket, only that matters. What is that area going to be? The big circle area minus the small circle area, which will be area here minus area here, that will be your dA. Okay. That is what it is supposed to be. So my fx has a value P plus dp by 2 times dA. Now I will go back and substitute that here. Every other value you know, A1 P and A1 will just become PA rho u square A. This will be having that P plus dp, A plus dA, all that. Okay. I will not write that full expression because we have less time. I will just go one term short. I will just simplify it one level and I will write it as I will write below here d rho I have written dA. Okay. Where this P dA comes from this fx, okay, and I have already cancelled the PA term coming from here with the PA term coming here. I have neglected all the multiplication of dA times d rho, all those quantities, that is what I have done. Okay. So, if I simplify this further, of course, this PdA gets cancelled, that is what I wanted to show from here. If I simplify this further, I will get to a point which looks like okay. Oh, there is a 2 which is very crucial, I missed the 2. There will be a 2 and du by u. Okay. Now, I go back to that corner here, mass equation. Mass equation, we know that this whole thing with coefficient 1 is 0. So, I will substitute the mass equation in momentum equation as we did before, then I will get to the final form, which will give me, I will just write one form smaller. I have cancelled the areas. In fact, I will take both the terms together to one side. I will get to this form, okay, and this happens to be your momentum equation in differential form in 1D flow. I do not have any assumption about constant area or anything here, while this other term, this one has constant area assumption. Okay. When I differentiate this, that does not give this, you notice that already. Okay. There is some difference between this, we will look at that next time.